So I'm going to be presenting some work that we gave it a pretty dry title of mode-dependent ray distortion optimized transforms. But really, this is mostly a way of explaining how graph signal processing concepts can help us look at very well-known and established concepts in a different light. Okay, so that's kind of the basic message here. And before I start, I want to make sure that the real author of this work, which is Lester, actually, who's in the back, is recognized. So this is really his work. And of course, since he's here, all the really hard questions, I hope you can, redirect to him. Okay, so I'll give a little bit of background on graph signal processing, and then we'll talk about three contributions. And again, the thing that I want you to keep in mind is that these are, as you'll see, they're very familiar ideas, but looked at from a somewhat different perspective. Okay, so in graph signal processing, we're defining a graph. In this case, the graph we're considering for this first example are line graphs. So we're still doing video processing. So think of each of these vertices as a pixel, and the edges, which in this case are all equal to 1, have weight equal to 1, correspond to some information about how correlated the pixels are or are expected to be. Now, with this, we can construct an adjacency matrix. In this case, the adjacency matrix is this one. It's pretty simple. Every pixel has a neighbor that is, and the edge weight is equal to 1. We can construct a degree matrix. Again, in this case, all the degrees are equal to 2, except at the two ends of the line graph. And then we have an additional matrix that gives us self-loop weights. So once we have this Laplacian, or generalized Laplacian, degree minus adjacency plus self-loop weights, if any, we can find the eigenvectors of this matrix, and this would be what we would call the graph-based transforms, or the graph-free transforms, and this is what we will be using for transforming the data. Okay, so the basis functions that we will use for the transformation will be the eigenvectors of a Laplacian. Now, these two examples, the one on the left gives us as eigenvectors the DCT basis. Okay, and you can find this in a very nice paper by Strang, basically 20 years ago. And this other example, where all we've done is added a self-loop in the first to the first pixel, corresponds to the ADST. So again, as I was saying, these are familiar transforms that we've seen, and they can be viewed from this graph perspective. Now, these graphs can also be interpreted from a probabilistic perspective, and that will link them to the KLT a bit later. And so you can think of a graph as a model that is a Gaussian Markov random field. When you have a large edge weight between two nodes, that means that the pixels, the corresponding pixels, have high correlation. The GFT on the graph signal corresponds to decorrelating the signal based on this probabilistic model captured by the graph. And designing the graph weights corresponds to finding the parameters of this probabilistic model. Okay, so keep this in mind. Now, if we go back to the two examples, the DCT and ADST, that single self-loop at one end makes the first basis function go from a constant, as you're familiar with in the DCT case, to this function that has a smaller value on the left. And if you're familiar with how ADST is used, that corresponds to the case that the first pixels on the left of the block are well predicted, and therefore they're more likely to be close to 0, right? So this simple thing, can be interpreted probabilistic as well. Okay, so we've done a bunch of work in this area. So you have a few references there, going from texture images to working with depth images, piecewise smooth, to intra and inter predicted video. In this talk, I'm going to focus on results with AV1 and AV2, and there'll be three areas that I'll cover. And again, this is kind of an overview of the various things that we've done. And as I said, these are all familiar ideas, but viewed from the graph perspective. So first, we'll talk about how to learn transforms from data. In this case, just the transform, not the whole pipeline of the codec, just the transform. Then we'll talk about what in a graph makes the corresponding transform fast. And then we will talk about how the graph representation of a transform helps us do better and faster decisions in RD optimization. Okay, so again, 3 familiar topics, but the graph perspectives give us a slightly different view of the problem. Okay, so we start with mode-dependent data-driven transforms. I mean, ideas have been around for a while, and for example, one of the earliest examples that I'm aware of was work by Efros, Chow, and Gray that looked at how to design a series of KLT transforms from data. And the way one would train a system like this is we would have multiple transforms that are competing with each other. Some might be transforms that are already defined, like DCT, and some may be learned from the data, or you may have more than one being learned from the data. And at every stage, you make a decision on which of the transforms is best, and then that changes the training set, and you redesign all the transform. Okay, so you have a training data, you do an assignment for each block in the training data to one of the candidate transforms. This then leads you to relearn the transform from that set of data, right? And again, you could have one fixed transform or more. You could have multiple learned transform. There are many choices. And when we think about this, we typically think about the KLT. So we have a bunch of blocks. For this set of blocks, we learn the covariance matrix and the eigenvectors of the covariance matrix as the KLT. Okay. So to do this, what we're going to do something similar. So this part is fairly close to standard techniques. So we want to introduce 1D transforms, and these 1D transforms are going to be combined with other 1D transforms. And so for intra-blocks, we use the mode for the selected intra-mode to decide what the training set for, and we will train one transform per mode. And for interblock, we realized that there's a lot of asymmetry in the error signals, the residuals, and so we learned both one mode-dependent, RD optimized transform and the flipped version. So we make those two as candidates, and these are used in combination with DCT. Okay, training data are 2D residues from AV1, and we use an approximation of rate distortion to decide what gets sent to each of the groups in the process of training. Okay, so far so familiar. Now, one thing we wanted to explore is what happens if we now introduce some regularization in how we learn the KLT. So instead of learning the KLT, which would be just using the eigenvectors of the covariance matrix, what we do is look for a Laplacian, such as the generalized Laplacians that I introduced in the first one of the first slides, that approximates the inverse of the covariance matrix under some regularization that makes it, a Laplacian. We have some work on this that was not specifically for video coding, and so we have 3 different possibilities. One is no regularization, so whatever the covariance matrix is, that's what we use as eigenvectors. 2 is we introduce a graph Laplacian constraint, but no particular structure to the graph. And 3, we now we force the graph to be a line graph. Okay, so sort of like the DCT, ADST, right? So pixel to pixel to pixel, and we only learn the edge weights and the vertex weights on that graph. Okay, so now when we do that, we start learning bases that look pretty similar. So I think if you had, after you're approximating the inverse of the KLT, which would have the same eigenvectors as the KLT, right? So the eigenvectors will be the same, and so we see that the basis looks similar, but what we find is that when we regularize with the line graph, the bases are more localized, and that's kind of interesting. We don't have an outcome where we use this in a more practical setting, but what it means is that maybe some transforms that are localized, sort of like wavelets might be useful for some residual blocks. Okay, one thing that I want to say is if you have large amounts of data, then there's probably not that much that you can gain by using something other than the KLT. But the KLT can be suboptimal if you don't have enough data, right? Because you're training all of these parameters with a limited amount of data. And so to illustrate this point, we have an example where this is compression gain in AV1, so it's all embedded there, and where we compare a setting where the transform is learned with different amounts of training data. And so when there is a lot of training data, then KLT does well. But when there is less training data, actually a regularized transform can be better. Okay, and I think that's something that if you're going to do data-driven designs, I think you have to be aware of not just how much data you have overall, but how much data there is for each of the pieces that you're designing, right? And in this example, if you have mode-dependent transforms, the amount of data for every mode is going to be quite different. And so potentially strategies should be different depending on how much data there is for each of those modes. We were trying to run this for even a lower amount of data, but we don't have results yet. Okay, so the number of parameters, if you think about it, for the KLTs of the order of n squared over 2. For the case of GFTs, it can be a lot lower. It's more of the order of n. Okay, so this can be something quite significant if you don't have a lot of data. Okay, one coding result where we used in this example the KLT, and this is embedded into the codec, and there is some gains. Whether that percentage is significant to you or not, that I don't know. But some of these things do help when embedded into a codec. Okay, so this was purely codec optimization. Now I'm going to switch gears a little bit and ask the question, well, what can we do about speeding up the transforms themselves, right? And one of the downsides of ideas such as the KLT is that you go from a really nice structure transform with fast algorithms such as the DCT to transforms that have no structure and no fast algorithms, right? And so we wanted to look at the problem of finding fast transform, but using the graph perspective to help us. Now, if you look at the DCT, remember that this is a line graph with all weights equal to 1. And you have a transform where you first have a butterfly operation with essentially weights 1 minus 1, and then you have combination of hard units, so plus minus 1 operations, and some gibbous rotations with some angles, right? Okay, now from a graph perspective, it turns out that to be able to create a butterfly unit like this one, okay, so with weights plus minus 1, all you need to have is symmetries in the graph. Okay, and so there's a direct correspondence with having a graph that has symmetries with being able to do this first stage. Now, why is this useful? Well, that first butterfly stage is very inexpensive, right? It's plus minus 1 operations. The root 2 parameters can be put at the end. And what you have here is that you divided the matrix that you need to compute that doesn't have structure by about a factor of 2. So the first stage saves you some computation, and instead of having an n by n matrix, now you have roughly n over 2, n over 2 by n over 2 matrices. Okay, and this is quite general. And for example, this can be applied for graphs that are line graphs that have symmetry in the middle. So in that example, you can see the two weights to the right of the symmetry point are the same. So it's E and E, and then C and C, B and B, and so forth, right? But also it can be applied for 2D blocks. And these are examples of symmetries that you can find. And whenever you have one of these symmetries, I guess you can say roughly a factor of 2 or so reduction in complexity. Now, of course, the beauty of the DCT is that when you do this first symmetric operation, you end up with graphs that themselves are symmetric again, right? And by exploiting this multiple times, that's how you get this n log n computation. Now, in examples such as these, for example, the one on the top, you don't necessarily have that after exploiting the symmetry and reconstructing graphs on both sides of the symmetry, you have you may not have a symmetry. Anyway, you can find a lot of details in this paper that just appeared in TSP, and I think there's some potentially interesting ideas to explore there. All right, so we've seen how to design transforms, how to speed up the computation of the transform. The last thing that I wanted to describe is how we use the graph structure to speed up the RD optimization. Okay, and this could be potentially useful for transforms, including DCT and ADST, which are very widely used. Okay, so if you think about a rate distortion optimization with the familiar Lagrangian cost, for every case, for every option you have for a particular set of pixels, you need to compute a transform. You need to do quantization and entropy coding, right? If you're doing this kind of brute force approach. Okay. So one thing that we wanted to think about is whether we can explore the graph properties to do some of this in the pixel domain. So that means we don't have to first compute the transform and then evaluate RD performance in the transform domain. Okay. So how might this be possible? So if you look back at the DCT, now this property is true for any graph Laplacian, and I'll spend a couple of minutes on it. If I look at this difference in the pixel domain, where here it's a very simple operation because the weights are all one, right? But for a general graph, this would be something like the weight between two nodes times the difference square of the nodes, right? So this is a sum that looks at the differences between pixels in the graph. You can prove that this is exactly equal to the right side. And what is the right side? The right side is the phi transpose x. That's the DCT coefficient. So it's a sum over all the DCT coefficients, the energy square for each DCT coefficient multiplied by lambda, which is each of the eigenvalues corresponding to those DCT coefficients. Okay? So if you think about it, this is basically a weighted sum of the energy in the frequency domain with some weight lambda that corresponds to the eigenvalues of the graph Laplacian for the DCT. Now, in practice, what we would like to do in terms of optimizing RD performance is we may know that, for example, the more energy there is in the high frequencies, the worse that representation is, right? So it turns out that these eigenvalues are also increasing. They go from 0 to increasingly larger numbers, right? So they penalize the high frequencies. Okay, so that means that if we do this, which is exactly equal to this, is sort of giving us some idea of what is the energy compaction in the frequency domain, except that we have these weights lambda that we cannot choose. Okay, so if you had some idea that you want the very little frequency in the highest frequency, but you don't care about how much energy there is in the low frequency, we almost have it, but we don't know these weights we cannot choose. Okay, does that make sense? So we have correspondence between something easy to compute in the pixel domain and a weighted sum of the frequency information. Okay, so that's always exact, but we cannot choose lambda. Okay, so the idea is to find a way to compute this, but with weights that we can choose. That's what we did here. So we extended the derivations in the paper by strength that I mentioned. Now this gives you, this is kind of a nice figure. It gives you the set of all sparse graphs that have exactly the same eigenvectors as a DCT, but different eigenvalues. Okay, so if you think about the DCT, it corresponds to this. It's a line graph, right? So you have pixels, 8 pixels connected line one to the other. You can reconnect these pixels in all of these different ways and achieve the same eigenvectors as a DCT, but with different eigenvalues, right? So what changes is what, for example, the lowest frequency in the DCT, or the highest frequency in the DCT may turn out to be a lower frequency in one of these graphs. And correspondingly, instead of the original lambdas, the eigenvalues of the original graph, this has different eigenvalues. Okay? So same eigenvectors, but different eigenvalues. And so what that means is that if you go back to this example, we will have these same quantities, the phi transpose x, but they will be weighting by different lambdas in each of those graphs. Okay. Okay, so what we would like to do is we want to estimate an RD cost that is a weighted sum of the frequencies at each, or the energy at each frequency, right? And what we want to do is create these W values that give us the desired set of weights. I mean, we don't know what those values are. Actually, we were, wondering what would be a good design. If you have any ideas, we'd be interested in hearing about those. And what we do is we find a linear combination of K graphs, that are all variations of the DCT graph with the same eigenvectors, and we combine these pixel domain matrix on each of these graphs. Okay, so this illustrates the idea. So to get some weights, we may compute a pixel-to-pixel difference on this graph, weighted by some factor, and a pixel-to-pixel difference on this graph, and combine it together, and then we get some arbitrary set of weights for the frequencies. And with this approximation that we proposed, this axis here is the index of the eigenvalue, and this is the index of the frequency, and this gives us the weight for each of the frequencies. Okay, so we can synthesize different sets of weights. Okay, now let me conclude, since I think I'm running out of time. So we embedded this again in AV1, and we looked at comparing these various transforms, in particular DCT and ADST. And the goal was to apply this pruning strategy to those transforms. And so, you have to choose one, you compute an RD metric, and so forth. So let me skip the details. So these are the results. Now we get results with that lower the encoding time with bitrate loss that is not as good as this method, which is based on neural networks, but is comparable to other existing methods. And one thing that I want to point out is that this approach is not data-driven, so it doesn't have to be trained. It just computes an approximation to this weighted energy, and it's much easier to interpret. So compared to prune to the accurate, whatever that is, it has of the order of 60 parameters versus 5,000 parameters. Okay, and again, no data for training. Okay, all right. So let me conclude with that. And so again, if you remember one thing about this, I know it's after lunch. It's a tough time to keep up with things. But remember that we were looking at DCT, ADST as line graph transforms, and that essentially we've looked at the learning a transform from data, finding fast approximations to a transform, and making RD decision, and looking at how a graph representation can help us come up with different designs, and in some cases, more efficient designs. And so with that, let me conclude. Thank you.
Thanks, Antonio. Any questions? Yeah.
So in the last topic, I didn't see that there is any quantization factor considered. So that is reflected in the weight.
No, there is no quantization. It's just a way of looking at. So I guess there's no there's not really rate distortion. It's just an estimate of how the frequencies are distributed, right? And so with some weights. And I think implicitly, if you have a good set of weights, that set of weights could reflect how much information in one frequency leads to some rate, right? So the weights themselves. So I mean, if you don't have any weights, right? I mean, you have an orthogonal transform, nothing has changed. So if you have some weights that are high for the high frequencies, that reflects the fact that if you have information in the high frequencies, that would lead to higher rate. So that you're penalizing the high frequencies, basically.
Okay, thanks.
Yeah.
Yeah. Thanks for Professor for the very interesting talk. So one clarification question. So it's how it's transform signal? It's additional options or replacing the original DCT and ADST?
In what, in the last piece of work, or which one?
I mean the first one, data-driven transforms.
No, I mean in the first one we're using we learn a 1D transform, and it will be used in combination with the other transforms. So it will be used for, maybe row-wise you use this data-driven transform, column-wise you use something else.
Okay, so
it's a replacement, yes.
It's a replacement.
Yeah.
So there's almost no runtime impact. I mean the encoder and decoder runtime.
I mean it just replaces one transform by another. I mean I guess depending on the kinds of transforms you have, the cost of the transform, the computation of the transform is more expensive unless you have some symmetry.
Okay, I see. So for the 0.7 gain achieved, is it using the fast transforms or? No,
that one is not the fast transform.
Okay.
I mean, the fast transform, you need to have a symmetry in the graph, and we've done experiments where we learn a transform, essentially we learn a graph from data, and we force that graph to have symmetries. And then you can exploit that initial stage of butterfly operations.
Okay, thank you.
Clarify a little bit. So I think the 0.7% gain is with the new transforms, those are signaled. So like everyone had 16 transforms before, now it has 24 transforms. I think it was presented in Sarah's talk yesterday. Yeah.
This one, Alexis.
So you also use quantization matrices. Are you thinking of extending, this kind of concepts with quantization matrices? Because like you have 24 transforms. Are you going to send quantization matrices for all of them, or is there a intelligent way to predict quantization matrices across each one?
We haven't really thought about that. So I don't know if Lester did some of that during the summer, but I don't know.
So I have a question about the last part. So how are the weights in the transform domain determined before designing?
Yeah, so I was saying, I don't think we have a good way of determining what the weights should be. We just know that they should be increasing with frequency, right? And one of the issues that I forgot to mention, it's not clear in the slides. One of the things we can do is we can use the weights that come from the DCT and then synthesize those same weights for the ADST, so that they're directly comparable. Because otherwise, if you just compute the differences on those two graphs, the weights which correspond to the eigenvalues of the graphs are different in DCT and ADST. So one of the simple things that I think we did was to basically make sure that the two sets of eigenvalues are similar, so that we can compare apples and apples, right? Because in the end, when you do the encoding, maybe the quantization matrices will be different, but in practice, you do penalize the higher frequencies, and probably you penalize them in a similar way from one to the other.
I would like to come back to the first question. How can you completely decouple your RD cost from quantization? Does it mean all your modes should be the same regardless of the operation point?
No. So it sounded like I claimed more than I was claiming. What I said is, let's say that you know that without modeling rate distortion, because if you try to do that, it's going to depend on the rate, right? So let's say you want something simple where you want to compare, option 1 versus option 2, and those options are two transforms, okay? And if you want a really simple model of what's going on, you know that the higher frequencies tend to require more bits, just in the way most systems are designed, right? And so let's say that you design from data, or you figure out a way of determining how large the penalty is for each of the frequencies. Those are the weights that we try to generate. But I'm not claiming that that's an optimal decision. We're just comparing energy, weighted energy across frequencies for two different types of transforms, and deciding whichever has the the lowest weighted energy, that's how we choose.
Great. Thank you very
All right,
much.
thank you.